Namaste everyone. Welcome to second PUC physics class. We were discussing about the conversion of galvanometer into voltmeter and ammeter in the last classes. Right now today we will see what is Bohr Magneton. And you know that any current loop is very similar to a magnet. Current loop in the sense any current carrying closed loop is like a magnet. If the current is in one direction, in clockwise say, it will act like one pole of the magnet, and if it is anti-clockwise it will act like another pole of the magnet. You know that a bar magnet contains north pole and south pole. Suppose the current is in this direction. Suppose you have a loop which carries current in the clockwise direction like this. Then you can find out the magnetic field in terms of this thumb rule or clasp rule in the reverse way. Now you have to assume the direction of current by the fingers, right? You have to allot it to the fingers. If the fingers represent the direction of current, then the thumb shows the direction of magnetic field. It is inside, into. So where do you get magnetic field into in the case of a bar magnet like this? So if this is a bar magnet like this, and if this is north pole and south pole, and if you are looking into the north pole, the magnetic field lines will be coming out like this, right? So out of the north pole. Whereas if you stand in the south pole and look into the south pole, you will find that magnetic fields are going in, whereas here they are going out, coming out. So if it is going in and this is equal to the south pole, so you can write it like this, south. You write yes and put some arrows, two arrows at the head and tail of the south. Then yes, then it is the south pole. What about if the coil is carrying a current in the anti-clockwise direction like this? The magnetic field is coming out, so it is out of the board, dot, into the board, cross. Then this is like a north pole, right? Out of the board means north pole. So if it is north pole, put some arrows. Is it right, anti-clockwise? So you can remember it like this. So when a coil is observed from one direction, one phase, if the current is clockwise and the other phase will be anti-clockwise, and you will have both north and south poles to the coil. So coil behaves like a magnet. Of course coil will not have a thickness, and if you want to have the exact replica of bar magnet, you have to go for solenoid, where coil is not wound at the same place, it is brought to a length, right? So it acts like a solenoid acts like a bar magnet. Okay, so now if you take an electron, now we will go to the basic loop. And if you have a current carrying wire, you know, when you pass current through the current carrying wire, so many electrons move around this. So if this is a wire and if it is connected to a battery like this, you know that current flows like this, right? Like this here. How do the electrons flow? Like this. Electron motion is the opposite to the direction of current flow. Unfortunately we have only electrons in a conductor, so their motion has to be taken opposite to the direction of current. Usually the direction of motion of positive charges is taken as the direction of current. So here you have to take the direction of current like this, electrons like this. Now when the electrons flow, there are plenty of electrons moving inside this, because this the potential difference created by the battery drives all the electrons, free electrons. So electrons move and current is seen. Now suppose there is one electron moving, how will be the case? It is also a current, it is a tiny current. Imagine a small electron moving around the nucleus, it is also equivalent to a current loop. Don't be under the impression that electrons must move only inside a conductor. Electrons can move by themselves, they need not have to have a conductor itself. Water need not flow through only pipe, right? It can flow in open space also. If you just pour some water from the top of the building, it flows down as if an object falls. So it need not have to have only a pipe, right? So electrons can move them by themselves in a particular path, and you know they can be made to move in a particular direction, in a particular path, by applying a magnetic field and all. So you can make the electrons to move. Now when an electron moves around a nucleus in a circular path or elliptical path, whatever it is it not a current loop? Won't it produce a magnetic field? Actually, if a material is a magnet, that magnetic property starts from that electron. So why does an ordinary iron piece doesn't behave like a magnet, and why does a magnet behaves like a magnet? What is the difference between them? Only this much. Every electron in a non-magnet like iron, and every electron in a magnet like another magnet, iron turn into a magnet, whatever it is. So a magnet and a metal both contain plenty of electrons moving around in a circular path around a nucleus. Now when they are moving around a nucleus in the circular path, they are the sources of magnet, and they produce a current and they produce a magnet, and we have to define a magnetic moment for them. And you know that magnetic moment is nothing but, so you will get so many terms after this. This is the end of the chapter, that magnetism, moving charges and magnetism. In the next chapter it is a continuation, magnetism and matter. There you will get plenty of terms and you will get confused with this and that. This is magnetic moment now, as if we have electric dipole moment, product of the charge and perpendicular distance between the charges. Here we have magnetic moment m is equal to, okay, I will write it as, okay, m is equal to I into A. Current into area gives the magnetic moment. There, charge into length gives the magnetic moment. One of the charge and perpendicular distance between the charges. Here current into area, charge by time into length, that is current into area gives the magnetic moment. So ampere meter square, its unit, ampere meter square, that is the unit for magnetic moment. Now, so if you go on testing all those electrons inside a material, you ask one by one electron, are you moving around the nucleus in a circular path? Yes sir, we are enjoying and we are moving around the nucleus. Are you producing any current? Yes sir. Are you producing any magnetic field? Yes sir, we are current loops. Each electron is a current loop. We produce magnetic field, and if the direction is clockwise, the magnetic field will be, if it is clockwise, then it is south pole, right? If the current is clockwise, then it is south pole, and if it is anti-clockwise, then it is north pole. So every tiny magnet moving around the nucleus is a source of, a tiny electron moving around the magnet is a source of, every tiny electron moving around the nucleus is a source of magnetic field. Every electron moving around the nucleus in the circular path produces magnetic field. But why iron piece is not a magnet? That is the question now. If you have so many plenty of electrons moving around the nucleus in the circular path, why can't iron piece behave like a magnet? Why should we magnetize it? Very simple. If one electron moving in a particular direction produces a magnetic field in one direction, another electron produces a magnetic field in the opposite direction, they cancel out. Net magnetic moment in the whole specimen is zero. The whole iron piece is not behaving like a magnet, but there are tiny magnets inside, and these tiny magnets are nothing but electrons. And if you can collect all the electrons in a molecule, you just go and list all the electrons in a molecule. What type of magnetism is produced? What type of magnetic field is produced by electron 1? Sir, I am producing it in the north direction, sir. What direction of magnetic field is produced by electron 2? Sir, my direction is south, sir. Another one is east, sir, west. So magnetic moments are aligned in different directions. But for a molecule, you will get a particular direction. If you sum up all the directions, you will get a particular direction. But in the neighboring molecule, it will be opposite. So the net magnetic moment of all the molecules will be zero, and the iron piece won't behave like a magnet. And now if you want to magnetize it, what you have to do is align the directions of all these dipoles, what I can dipole, because it has got a north pole and south pole ends. Align the magnetic moment of all these dipoles in a particular direction. Then that specimen behaves like a magnet. Who will do this job? Aligning all the dipoles which are in the random directions to a particular direction. Apply another magnetic field. All these dipoles will turn their magnetic moments in a particular direction. Now the specimen turns to be a magnet. That is what we did when we were kids, right? We used to take an iron piece and rub it against a magnet. What do you mean by rubbing it against a magnet? Just bring that iron piece very close to the magnet, that's all. When you bring the iron piece very close to the magnetic field of magnet magnetizes the iron piece. What do you mean by magnetizing the iron piece? Aligning these dipoles in a particular direction, that's all. So now we have to learn, that means we have to learn the magnetic field of an electron, which is very, very important. So all the magnetic property starts from electron. You may have a question, sir, nucleus has a positive charge. The positive charge of the nucleus is because of the protons. Won't the protons produce magnetic field? They will have spin motion and orbital motion inside the nucleus, but their contribution is very less, because you imagine an electron moving around the nucleus in a circular orbit. Of course, it is very tiny. You know the radius of the electron in the order of angstroms, right? Radius of the path of the electron, not the electron. Radius of the path of the electron is in the order of angstroms, 10 to the power minus 10 meters. And the size of the nucleus is very small, 10 to the power minus 15 meters. And what area they will cover, protons will cover inside the nucleus, what may be their magnetic moment, area is very less. So contribution of protons to the magnetic moment of the whole specimen is very less. Contribution of electrons is more. And even in the electrons, if an electron is revolving around the nucleus, this is nucleus, and covering an area A and producing a current I, electron will produce current in two ways. One is motion around the nucleus, revolution. Another is spinning. It will keep on spinning as it moves. And won't spinning produce current? Yes, it will produce current. Won't spinning produce magnetic field? Yes, but that contribution is again very less. So magnetic moment created due to spin motion and magnetic moment of the nucleus created due to protons is neglected. Magnetic moment contribution due to orbital motion of electrons is only taken into account, because other values are very, very less. So magnetic moment of electrons due to orbital motion is much, much more than the magnetic moment due to their spin motion and magnetic moment due to the orbital and spin motion of protons inside the nucleus. Those things are very less and you can neglect them. That is why we are taking the magnetic moment of orbital motion of the electron. So now this is the introduction. You need not write all these things. Just understand what we are studying. Why do we study all these things? That is very much needed. So the magnetic moment of electron, when it is applied, you take the simplest electron. It is the first electron moving around the nucleus of hydrogen atom, innermost electron. When we find out the magnetic moment of the innermost electron of hydrogen atom, that is the first orbit of hydrogen atom, what is the magnetic moment called? It is called Bohr Magneton. Bohr Magneton is the magnetic moment of the electron in the innermost orbit of the hydrogen atom. That is the simplest possible way, simplest possible magnetic moment, and that's why it is given the name of Bohr Magneton. So now how to calculate the magnetic moment of the first orbit of hydrogen atom, and that is due to orbital motion. Spin motion it is neglected because its contribution is very less. Okay, you can do it very easily. You have to start from, actually the derivation in the book starts from something else, but you have to keep it in mind. What is magnetic moment? Magnetic moment is the product of current produced into area of the loop. If you are applying it to a circular wire, circular loop, we define magnetic moment as the product of current into area. But when it comes to the question of an electron, we change the symbol. We write mu, magnetic moment of an electron. And we know that an electron can produce current and produce magnetic field because of two motions. One is spin and another is rotation. And spin motion is producing a very small current and its contribution of magnetic moment is less. We neglect it. We collect the magnetic moment only due to the orbital motion around the nucleus. So orbital motion is always represented by L, mu L. So we changed the symbol. In general terms, we write magnetic moment as capital M or small m. Here we represented it by mu, saying that we are calculating the magnetic moment of electron only due to orbital motion. L is equal to current into area. You start from this formula. Current into area gives the magnetic moment. We use this in current loop, right? Circular loop, getting twisted, current into area. Right. So if this is I into A, sir, what is I? Current produced by the electron. You imagine, and you have to draw this diagram actually. So imagine the nucleus. I don't write the charge of the nucleus. This is the electron revolving around the nucleus. Let this be the direction of the electron. If that is the direction of electron moving in the circular path, what is the direction of current? Is it not this one, right? That is the direction of current. This is only the path I have shown. It is not the circular wire, right? It is not a circular wire. Electron is moving by itself because of the centripetal force. Now, if the current direction of current is shown by the fingers and thumb gives the direction of magnetic field in a circular loop like this, that means magnetic moment here is into, right? So I will show it here. It is into. In the book it is shown like this. Magnetic moment. See, these symbols you will have to understand. You have to all these terms. If you are by-hearting this derivation, all these terms become very, very ugly for you, and you will struggle to remember what is mu, what is suffix L, and why it is cross, and what is this arrow mark, what is that vector. Magnetic moment is a vector quantity. It has a direction. See, direction, current, magnetic field direction, magnetic moment, right? So mu L. So magnetic moment due to an electron revolving around the nucleus is like this. So I have simply shown the direction here, that's all. Now what is the formula for this one? Let r be the radius of the electron moving in the circular path, r. Now if you want to fill the values for this, get ready with what is current, what is area. Area is of course, A is pi r squared, no doubt. Okay, what is current? Let the electron complete one full circular path. How much time does it take? It is called 1 period. When the electron completes one full circular path, the time taken to complete one full circular path is called period. So I can write current due to an electron is rate of flow of charges, charge flowing per second. Now if you stand here and observe the electron, right, how many times you will see the electron in t seconds? In t seconds, how many times you can see the electron? What is t seconds, capital T? It is the time taken to complete one full rotation. If you wait for a time of 1 period, you can see the electron once, because it completes one full rotation once. So 1 electron is flowing. What do you mean by current? Current is rate of flow of charges. How much charge flows in per second? Now in t seconds, capital T, 1 electron has moved. What is the charge of 1 electron? E, 1.6 into 10 to the power minus 19 coulomb. I am writing only the magnitude plus. Even though electron has got a negative charge, I am writing only the charge, because I know that current direction is like this. It is ulta. So did you get what did I write here? Current means rate of flow of charges. It is a charge flowing per second. If it is charge flowing per second, you take capital T, that is time taken by the electron to complete one full circle. When you observe the electron for a time of 1 period, you come across only 1 electron. If you observe it for 2 periods, you will get the same electron twice moving. So total charge becomes 2 times the charge of electron. Now you come across only 1 electron. So E by T. Now what is T? Period. How can you write period as? Of course, you see, you shouldn't forget that we are filling this formula. Otherwise this derivation becomes simply a mess up. You have to search all the items required for this formula. I into A. I is Q by T. But what is Q? E. And time taken is 1 period. What is T? T can be got like this. What is period? You see, if V is the speed of the electron, because we know the speed from the that atomic theory of Bohr's atomic theory, V is equal to velocity of the electron is equal to 2 pi r distance travel divided by time taken. So what is time? 2 pi r by V. So we are ready with T, we are ready with the area. Oh sorry, here you have to finish it. We should be ready with current. Current is rate of flow of charges, that is 1 electron flowing in 1 period, and T is 2 pi r by V. So E divided by charge of electron divided by 2 pi r by V. Right? Now substitute it here. What is angular momentum of the electron? Orbital angular momentum of the electron. This may be in any orbit now. Then we will apply it to the first orbit of hydrogen. The angular momentum, the magnetic moment due to the orbital motion. It is magnetic moment due to rotational motion is current. Current we have got it as EV by 2 pi r obtained from this equation into area. Area is pi r squared. Okay? I think you have got this. Current is rate of flow of charges, 1 electron moving in 1 period. That means you get only 1 electron charge, but period is distance by velocity. Distance is 2 pi r by velocity is V. So EV by 2 pi r into pi r squared. I rub this because I want this space to continue. Okay. So this is the basic formula which is needed. So fill it with the required formulas. Okay, here I have to use the same pi r square. 1 r gets cancelled here. 1 pi gets cancelled here. So I get EV divided by 2. EV divided by 2, EVR divided by 2 gives, only 1 r is cancelled. EVR by 2 gives the magnetic moment. Magnetic moment produced by an electron which is moving around the nucleus. Now, you know Bohr's theory, saying that Bohr says if an electron is moving around the nucleus and if it has to have a particular orbit, stationary orbit, fixed orbit, then there is a condition satisfied. That is, its angular momentum L must be equal to nh by 2 pi, and which is also equal to mvr. The angular momentum L is equal to nh by 2 pi must be equal to mvr. And if mvr is not equal to nh by 2 pi, where n can stand the values, have the values 1, 2, 3, 4, only integral values, there are no fractions possible. So if you can recall that atomic theory, the angular momentum must be equal to mvr must equal to nh by 2 pi. And if you want to get that part here, what I can do is, I have Vr, correct? I don't have nothing, m. So what I can do? Divide and multiply by mass of the electron. Okay, I can write m. Divide and multiply by mass of the electron. So what can I change in this formula? The magnetic moment due to orbital motion mu L is equal to, of electron is equal to mvr. That means E by 2 m. Charge of the electron, okay, I'll write charge of the electron by 2m into mvr, that is angular momentum L. Angular momentum is moment of momentum mv. Hope you have followed this. So L into E by 2m, this is magnetic moment. Okay, not over, still we have something to do with this one. I'll rub this, and at a stretch I will do it again, okay, at the end. So magnetic moment due to an electron revolving around the nucleus in a circular orbit of radius r is E by 2m into L. L is nh by 2 pi, you know it. It is mvr. Now, if you bring L here, the magnetic moment of electron divided by this, what is this? Magnetic moment divided by angular momentum. I will write it here. Magnetic moment, okay, moment, I into A divided by angular momentum. I don't know why that word is missing from my tongue. Angular momentum. This is called, this is not called Bohr's Magneton. This is called by another name, and that is Gyromagnetic ratio. Yes, Gyromagnetic ratio. So it's not a very, very important question for the sake of exam. If you are asked what is gyromagnetic ratio, the ratio of magnetic moment of an electron to its orbital angular momentum. So magnetic moment to the angular momentum is called gyromagnetic ratio. Remember, this is mu. Okay, and if you want to find out what is its value, so mu of electron due to orbital motion by orbital angular momentum is equal to E L by 2m. And what is its value? If you want to write the value, L is equal to nh by 2 pi. I can substitute E by 2m into nh by 2 pi. Okay. If the electron is in the first orbit of hydrogen atom, then you can substitute n is equal to 1, right? Or shall I substitute some other values? So mu L, no, L, why did L come here? There is no L here. E by 2m only, right? E by 2m, that's what I was. Mu L by L is equal to E by 2m. So find out this value. 1.6 into 10 to the power minus 19 coulomb. 2 into 9.1 into 10 to the power minus 31 kg. So what is that gyromagnetic ratio? Mu L by L, that is equal to gyromagnetic ratio value. Let me calculate it. Its value is 1.6 by 2 is 0.8. 0.8 divided by 9.1, that comes to 8.79 or 8.8 into 10 to the power, here is 0.08, so you will have 10 to the power minus 2 extra, plus 31, minus 21, 10 to the power minus 10. This is, I will write the actual value. Today my mind is not working so well. 0.088 into 10 to the power minus 31 plus 31, it is 12, right? 0.088 into 10 to the power 12. Can you write any unit for this? It is the charge by mass, coulomb per kg. Finish. This is gyromagnetic ratio. It is not Bohr Magneton. So what is Bohr Magneton now? So this is an intermediate derivation, a diversion here. Suppose you want to know what is Bohr Magneton, you continue it like this. So we will continue it from mu L is equal to L into magnetic moment of an electron due to orbital motion is equal to L into E by 2m. Substitute for L. If the electron is satisfying Bohr's quantization rule, h by 2 pi, E by 2m, and substitute the value. Now this is the magnetic moment of electron in any orbit. Put n equal to 1, it is in the first orbit. Put n equal to 2, it is in the next orbit. Now apply this to the simplest atom, that is Bohr's model, that is the hydrogen atom. The first orbit of hydrogen atom, put n is equal to 1, then mu L is equal to He by 4 pi m, right? He by 4 pi m, that is equal to 6.6 into 10 to the power minus 34 into 1.6 into 10 to the power minus 19 divided by 4 into 3.14 into 9.1 into 10 to the power minus 31. Find out the value. This is called Bohr Magneton, and its value is 6.6 into 1.6 is equal to, you can check it, divided by 4 divided by 3.14 and divided by 9.1. That comes to 0.0923 into 10 to the power. So here we have minus 31 plus 31 minus 3, right? Minus 31 plus 31. Did I substitute everything? H Planck's constant, E charge of the electron 1.6 into 10 to the power minus 19, mass of the electron, plus 31 becomes minus 3, and minus 3 plus 9, minus 22. 9.23 into 10 to the power minus 24. That is the ampere meter square, because it is magnetic moment. Ampere meter square. I into A. It started from I into A. So current into area, ampere meter square. This is Bohr Magneton. So what do you mean by Bohr Magneton? Magnetic moment due to, or magnetic moment of the electron in the first orbit of hydrogen atom. That is called Bohr Magneton, and its value is given by this one. So this is the derivation. Once it was asked, I can't say that this is a very unimportant derivation. It may be important because once it was asked for the exam. So I will do it a stretch once without much explanation. So the magnetic moment due to an electron due to its orbital motion around the nucleus is called Bohr Magneton. And if you consider an electron moving around the nucleus in the anti-clockwise direction like this, then the current due to it will be like this, and here the magnetic moment will be cross, because current is like this. So this is the magnetic moment direction. And if you want to calculate the magnetic moment of electron, mu, due to orbital motion, that is rotational motion, is equal to, then it is current into area. And what is current? Current is nothing but charge by time. So this is a charge to time ratio. Charge is E, and one electron can be seen in 1 period. And area is nothing but pi r squared, where r is the radius of the circular path. Then magnetic moment due to the orbital motion is given by E into pi r squared divided by t, period. Period is nothing but, so velocity of the electron or speed of the electron is 1 full circumference divided by time taken is called 1 period. T is equal to 2 pi r by v, So I can write it as 2 pi r divided by v. So 1 r gets cancelled, 1 pi gets cancelled, it becomes EVR divided by 2. That is the magnetic moment. But you don't have m here to express the angular momentum, mvr, nh by 2 pi. So multiply and divide by mass of the electron, then mvr, you can club them together. So what you will get, magnetic moment due to the orbital motion is equal to E by 2r into the angular momentum L, because L is equal to mv, mass of the electron, mvr. Yes, and if you get this mu L by L, then it is called gyromagnetic ratio. Magnetic moment of the electron to the angular momentum of the electron. That ratio is called gyromagnetic ratio. It is E by R. You can calculate E by 2R. You can calculate its value. But if I want to know what is the Bohr magneton, take this one. Mu L is equal to E by 2R into NH by 2 pi. Because L is equal to NH by 2 pi. If you are concentrating on the first orbit of hydrogen atom, put n equal to 1. Then mu L is equal to E H by 4 pi R. Substitute the value, you will get Bohr magneton. So magnetic moment due to an electron in the first orbit of hydrogen atom is called Bohr magneton. So this chapter is a very important chapter, but somehow we were not able to complete it at a stretch. We had some part before COVID and some part after COVID, and in between COVID, not after COVID. And we will have exam after COVID, right? And we pray God that this will come to an end very soon. Of course, classes will start, I think, by next month. We will see that. And you have to be very careful about all these things, because once the classes start, again and again I say, you will not get any time for anything else. So that completes the chapter. We will work out some problems in the next class, and again we will go for some entrance exam questions also in between. But I think we will have to complete the next chapter and then go to the entrance exam problem, because it is also related to this. It is not a separate chapter. Okay, thanks for watching my class. We will meet in the next class with a lot of problems, and then we will go to the entrance exam problems. Take care of your health, don't waste time, and hope you are using all these videos. Thank you.